So this will be our first 3 sample questions for this semester. The TA has divided their labor, and then they will meet you in the time slot, and then they will work out these 3 sample questions for you, and also they will answer your questions regarding the course content. All right. So secondly, I have also sent out problem set 1 this morning to you. The due date is about 2 weeks, just I think after the airdrop period. So the mobility should have been settled by then. And then there, as I said, there is a buffer of 2 days. If you are too busy to meet the deadline, you can still submit your work within 2 full days, and there will only be a discount of 20% on your marks. I really encourage you to try out all these problem set questions. They are designed to help you learn. Actually, I filter in a lot of things that when you read the questions, you can learn more quantum mechanics. Okay, so you have works to do. The TA also has work to do. They have to work out the solutions to the sample questions before they can meet you. All right, so last time we already motivated the first part of our course. The first part of the course has to do with some approximation methods. We want to build up your toolbox so that you have a few skills, making approximations in hand. Then we will discuss how to apply them to understand the details of atoms, molecules, and other matter. So that is the plan of the whole course. So first of all, we will build up our toolbox. So today, I hope that we can do 2 things, at least part of the second thing. The first thing is not an approximation method. The first thing I would like to do is to turn the time-independent Schrödinger equation problem into a huge matrix formalism. I'm sure that you have seen that in Professor Liu's course last term, okay, the Quantum Mechanics 1. If not, don't worry, it's just a few steps. And more importantly for our course, it is the resultant big matrix that is more important than the procedure of getting that big matrix. For the procedure, I hope that you try to do it once, and only once in your lifetime, because the result won't change. I hope that after you believe in that result, you can grab it and start to move on and see some more interesting physics. Okay, so that's the plan of today's lecture. I have posted the class notes in the course page within the department site. So let me share the screen. You see a page? I think so. Okay. So this is the very first step. As said, I would like to turn this time-independent Schrödinger equation, which is of this form, into a huge matrix problem. So let's digest what is the problem, okay? Now you give me a quantum problem, meaning, say, a particle under the influence of some potential energy function, like a trap in a box, trapped in a harmonic oscillator, or trapped by the Coulomb attraction as the electron does in a hydrogen atom. So you give me a system by going through standard steps, for example, think what happened classically. So you have a kinetic energy part, you have a potential energy part, put them together, that will become the Hamiltonian. And then you go quantum. There are operators for you to plug. The momentum operator takes on a form, the position operator takes on a form, thereby you have this Hamiltonian operator, H hat here, okay? So I hope everyone is following me at least up to this point, okay? It's too early to get lost, okay? So do we have a common footing? Okay, you follow what I'm saying? Okay, great. So H is related to the problem. You have to give me a problem, then I start working, all right? So H. Then let's look at this Schrödinger equation, especially this time-independent one. We started off with the time-dependent one and realizing that particular problems and many problems of this form, that the H is independent of time, then we can do so-called separation of variables. We have this time-independent Schrödinger equation, okay? Now, it is a very important equation and very interesting equation. The equation is, you give me the system, then I write down H psi equals E psi. All right, so what are we solving? We are not solving only for the E, where E will represent the allowed energies. Now, there is an S there, okay? So it's one equation to solve for many allowed energies of the quantum system. All right, now, if you get lost, don't worry, think about particle in an infinite box. One system, there are infinite many allowed but discrete energies. You see, one equation gives you many, usually infinitely many allowed energies of that system. In high school, you have learned hydrogen atom. It is one quantum system, one Hamiltonian, then you have infinite many allowed energies. Okay, the bounded ones are minus 13.6 EV divided by n squared, and n is 1, 2, 3, 4, 5, so you have infinite many, all right? But not only that, the Schrödinger equation here also solves for the so-called energy eigenfunction or eigenstate, the phi. So basically, this equation is to solve for many pairs of E and phi. Okay, I type it in the box, all right? So you will solve some phi that will be the allowed wave functions, meaning satisfying some boundary conditions, as well as this equation, okay? And for each of these wave functions, allowed ones, there is a corresponding E value, that is the allowed energies, the allowed values of the energy, okay? So it is a profound equation, one simple equation, only 4 things, H psi equals E psi, that basically help us understand a big part of the physics of the material world. All right, so this is a big part of quantum mechanics 1. You fill in a lot of techniques, but at the end, this is the governing equation, okay? The goal here is to try to solve it, okay? As I motivated last time, very often, the interesting and real problems in quantum mechanics are not exactly solvable, meaning we know the equation, this one, but we can't solve it analytically. Even your mathematical skills are extremely powerful. Sorry, okay? So helium atom, for example, no one can do it, okay? So that's why in this first module, we want to develop some approximations. This is our first step. We want to do something exact. So how to do it? We want to first turn it into a huge matrix problem, okay? So to start, we have a choice. We need to make a choice. The choice is that we inspect the problem defined by H. For example, what is the domain that the particle will live in? Okay, how far in space that you can find the particle, for example. And then you make a choice of a basis set, so-called basis functions, okay, a set of basis functions. Well, usually it is an infinite set, all right? For example, last time I mentioned several problems that you cannot solve exactly. Infinite weld with a tilted bottom, okay? Or an infinite weld with some wiggling in the potential inside, okay? So, however, you know how to solve this infinite weld. Exactly, okay? Realizing that in all these cases, the wave function will be zero outside the box, non-zero inside the box, okay? Therefore, if you take the exact solutions of this infinite weld with a flat bottom to be your basis sets, that will be a good choice. Because what you are going to find, the wave function is non-zero, also in the same region that these basis functions are non-zero, okay? So that is some art and science in choosing a proper or good choice of the basis function. Nonetheless, if it is a lousy choice, as long as the coverage, the range of the domain is okay, it still works. Okay, so here we have a choice. We said that, okay, we have picked a choice. I will call this basis function phi1, phi2, and so on, okay? This is PHI, okay? This is phi, okay? The wave function is psi, okay? So different thing. All right, so in short, I will represent this whole set of basis function in this curly bracket, okay? So that is a shorthand. So now we have two things in hand. We have the Hamiltonian, the problem. We know the equation that we want to solve, and we have made a choice of the basis function, okay? Then we start turning the Schrödinger equation into a big matrix problem. Okay, so this is the example that I mentioned. All right, so this is hard to solve, and therefore we have to do more work on it. But we know how to do this, so we have an infinite set of functions here that will be a good choice for the basis function to handle this problem. In doing so, we will make an expansion of the unknown energy eigenfunction of the hard-to-solve problem as a linear combination of the basis functions. Okay, so look at this equation, for example, A2. All right, now this is unknown, we want to solve. We pick a choice, okay? We make a choice of the basis function, so all these are known, it is our choice. What are the unknowns? The coefficients, the expansion coefficients. Therefore, we have to set up some way to solve for these coefficients If we can solve this, we know the energy eigenfunction, and we can also know the energy eigenvalue, E. Okay, so that is the strategy. Before we do the mathematics, it's always good to know what is the physics that, for that you are doing the mathematics. You understand my sentence? I hope. Okay, so just take this example. You know this exactly solvable problem. And then you have a ground state, you have the first excited state, you have the second excited state, and usually you start labeling them 1, 2, 3, 4, 5, and so on. And the lower indices, 1, 2, will be less vaguely. Okay, the ground state is just that. The first excited state is a sign with one node, the second excited state. So increasingly vaguely. Okay, so it is a point that is good to keep in mind. Although the mathematics doesn't require us to know that, but we are not doing mathematics, we're doing physics. Okay, for example, if we are trying to look for the ground state of this funny looking problem, we would expect the ground state should be less vaguely than the first excited state of this funny problem. Therefore, when we do the expansion for the ground state, we have some expectations, right? The less vaguely bases will have a higher weighting. So the coefficient, we expect it to be bigger for the less vaguely one, and then may be decorated by some still less vaguely components, so that at the end, we get the wave function, the ground state of this problem. Okay, so guys, do you follow what I'm saying? Okay, now this is physics before mathematics. Okay, so usually we have this idea. A common ugly set is plane waves. Okay, and then we always start with plane waves with longer wavelength, then shorter, then shorter, then shorter. All right, so again, it's less vagueling, more vagueling, widely wiggling, things like that. Okay, so with this in mind, let's do the maths. This is the equation we want to play with. Now we pick our bases. First step, expand the unknown eigenfunction into the bases. Okay, I'm afraid that you get lost, so I always label to you that what are the unknowns. Now, suddenly we switch the unknown from the eigenfunction phi to the many unknowns of the coefficients AI. If we know AI, we can compose back the wave function. Okay, now this expansion, as long as this so-called basis function is a complete set, then it is exact. All right. In physics, usually we don't worry about proof of completeness. We leave it for the mathematicians. In physics, keep on going with the problem. The answer will tell you whether your choice of basis function is good or bad. The answer will tell you, because we are handling physics phenomena. Okay, your result will tell you whether the result makes good physical sense. And that is, I think, a good way to do physics. Okay, so now, good, we are ready. Next step, plug this wave function expansion into the Schrodinger equation. Okay, so it is this line. Okay, H psi, so psi is the sum. the AI is a constant, there are coefficients, unknowns, but nonetheless, the operator will not operate on them. All right, so it goes through the operator, and the H only operate upon the basis functions phi I. Okay, that is the left-hand side. The right-hand side, the unknown is E, the energy, but it is a number, it's a value. Okay, so I just multiply into the E, the expansion. Okay, do you follow me up to this highlighted line? No questions, right? Easy. Okay, the next step is the most important one. Okay, pay attention. Okay, once in your lifetime, follow me, please. Now, we have a basis set. Okay, so we have many of this. Now, you from your set, pick one. Okay, pick any one. Pick one, call it J. Okay, then turn it into its complex conjugate. Now, because in quantum mechanics, we can play with complex functions. Okay, so pick one, phi j, make it a complex conjugate, and then multiply on the left. Left multiply means this thing. Multiply it in the equation here and here. Okay, that is left multiply. All right. So follow me. This appear on the left-hand side of the H operator, and that appears on the left-hand side of phi I. All right. Second step, integrate over all coordinates. So that's why I have these integrals. Okay, do you understand how I get A3? Oh yeah, if you have questions, raise it now. You will have to do something like that quite often in approximations as well. Is that okay? And now, let's look at the whole thing, okay? I just want to remind you what are the unknowns. We want to find the coefficients so that we can construct the unknown wave function phi psi. Also, we want to find the energy E, okay? So those are the unknowns. What are the knowns? You give me a problem, H is known. I have picked my choice of function. The set is known. So all these integrals are known. Okay? So now I want to introduce some symbols for these integrals. But let me repeat. You give me a problem H, I make my choice, then the two integrals here, actually many integrals here, are already known. Known by that, I mean you can write a program to calculate every one of them if you don't want to do it analytically, okay? So now I want to introduce some symbols to represent this. For example, I will call this integral as Ji. Reasonable, right? There are two indices, phi I, phi j star. So the result depends on which phi I and which phi j are involved in this integral. Okay? There are two indices. and that motivates us that we are actually handling a matrix problem here, all right? Similarly, I'm going to call this integral, you see, you give me a problem H, I have a basis, I pick a J to the left and I on the right, do an integral, again, two indices. Therefore, I'm going to call this H, J, I. Okay? Follow me? Yeah. Okay. So let me see. Okay. So here I will call this integral as Ji. Okay. Now some students may wonder, is it delta Ji? Okay. That is to say, you may question whether my chosen basis functions are normalized and orthogonal to each other. If they are, then Sji indeed will be a Kronecker delta function delta Ji. Because if they are the same, normalization means the right-hand side is 1. If they are orthogonal, this integral will give you 0, okay? However, at this point, I would not assume our chosen basis to be orthogonal or normalized. Normalization, yes, we can always do that, okay? Let's say for the time being, I'm lazy. I don't want to normalize my basis set, but normalization poses no problem. We can always do that. However, orthogonal, okay? Pay attention here. I'm not assuming the basis functions to be orthogonal here for a good reason. Sometimes in quantum mechanics problem, I really need to choose some basis functions that are not orthogonal. An example is the following. I want to consider hydrogen molecule. All right. So physically, we have a nucleus here, we have a nucleus here, we have 2 electrons. Okay, so do you see something on the screen? Okay, good. All right, so it's working. All right, so now I want to approximate a ground state wave function for the electrons living in a hydrogen molecule. All right. Now, a very reasonable choice will be, let's start off with some atomic function of the hydrogen atom. So I'm thinking about a 1s atomic wave function of the left-hand side hydrogen and a 1s atomic wave function of the right side hydrogen atom. Okay? Follow me? So I will have a phi left-hand side of 1s, and then I will have a phi right-hand side atom 1s. Okay? That will be a good choice of a small basis function to start approximate my ground state of a hydrogen molecule. Okay? Now, they belong to different centers, left and right nuclei. Follow me? 得唔得？行不行啊 ？OK 唔 OK 喂 ？OK。Now, the point I want to make is that if you think about the integration of left star right, integrate over all space, it is not zero. Because the two 1s wave functions belong to different centers, different nuclei. Okay? So to prepare for such situations, I would rather not assuming orthogonality. All right? So I not here stated clearly. Thereby, I will simply call this thing a symbol SJI. Okay? Now, if they are normalized, then the diagonal II will be 1. Okay? Nonetheless, they may not be orthogonal, so off diagonal SJI will be not 0. Okay? Done. How about this? The other one on the left-hand side of the equation, similarly, it carries two indices, so I call it HJI. All right? So let me go back to the previous equation. After using these symbols, the equations becomes this. Okay? This is equivalent to the Schrödinger equation. We have not made any approximations. Okay? So equivalent in Chinese is 等价, 等价啦, okay? And then if you like, I can write all the things onto the left-hand side. So thereby, this is also equivalent to the time-independent Schrödinger equation. Okay. Again, to remind you, what are the unknowns? The unknowns are all these coefficients and the energy. Okay? Keep track of what are the enemies. Okay? We want to solve this and that. Okay. So now we are done. We succeeded. We have turned the Schrödinger equation problem into a big matrix problem. Okay? Now I'm afraid that some of you may not immediately realize that this is a big matrix problem. Okay? So, refresher. Okay? Now for those who know, just 2 minutes, okay? Take a rest. Okay, now, consider a 2 by 2 multiply into a column A1, A2, okay? So A1, A2 is similar to this A. Of course, you know how to multiply 2 by 2 into 2 by 1. It will give you a column 2 by 1, all right? Again, the first one will be this multiply into A1 plus this multiply into A2. So that's the first line, okay? So we have a common footing here, right? Now, write it in some less transparent way, unfortunately. So the first row up here, see my cross, okay? Actually can be written as a summation M1I AI, okay? The second line, similarly, is a sum over I, but the first index, what we are going to call it J, will be 2. So M2I AI. So therefore, these two things separately can be represented by a sum. This one, in particular, when J is 1. Okay, remember we pick a J. Okay, meaning if we pick J being 1, we will get the first row. Okay, second row is J equals 2. All right, so now let's go back. We have this equivalent to the Schrödinger equation. Okay, now if we write it in the long form, it is this big matrix problem. I have nothing to explain because it is identical. Okay, spend 10 seconds, stare at it. Convince yourself that it is the case. Okay, so any question up to here? This is the punchline. So we succeeded. Schrödinger equation, only 4 symbols, suddenly implementing a big matrix problem. Okay. Any question? Looks okay. All right, so this is the take-home message. All right, if you don't want to know anything in between, don't worry. If you know this, you can move on. Okay, the point is, starting from H psi equals E psi, pick a basis, then the next step is this big matrix. Okay, it's very easy to remember it because all the matrix elements, that is to say, each entry of the matrix takes on the same form. It is Hji minus ESji. So you can calculate these two integrals and then you can compose every element. Okay? In principle, no problem. What are the enemies? We want to solve this column. And more than that, we want to solve these values for E. Okay? Again, remember, at the very beginning, we know that it's not only one set, one column of AI that we are going to solve. No. There are value E and psi pairs. So we are expecting there will be many values of E, and then for each one of them, there is a corresponding eigenvector. Okay? So now life will become easier. We want to solve for E. How? Okay? Non-trivial solutions, meaning I see a trivial solution here. It's 0, 0, 0, 0, 0, 0. Do you see? All the coefficients are 0. That is not a good solution. The particle disappeared. The wave function is 0. Okay? You destroyed the particle. Okay? That is bad. So we look for non-trivial solution. That is a fancy word of you don't destroy the particle. Okay? So now, you don't want this to be 0. Therefore, matrix mathematics says the determinant of this infinite by infinite stuff should be 0. Okay? Now, noting that there are E in all the entries, you multiply this thing out. For example, let's say it is 3 by 3, smaller. You multiply it out, it's a cubic equation for E. Okay, do you see this one? You are so quiet. Do you see that? Okay. So if you just think about it as 3 by 3, it is a cubic equation. Therefore, there will be 3 values. Extending it, if you think about it as 5 by 5, it will be patented, I think that is the term, is that a fifth order equation for E. Therefore, you will get 5 values of E, okay? Simply put, the size, the square matrix will give you that many eigenvalues, okay? So now, if it is infinite by infinite, you will get infinite number of E. That makes sense. You know that problem. Infinite well with a vacuum base will have infinite many, right? Ground state, first excited, and so on, okay? Makes sense, all right? So everything is there because we have not made any approximations yet. Here, now, that is the key point up to here, all right? Now, the rest is trying to simplify things, okay? Make life easier. First of all, in the previous term, you learned that the Hamiltonians we encounter are Hermitian. They give real eigenvalues because energies are real, okay? And for that reason, we have a relationship between Hji and Hij star. They are equal because H is Hermitian, all right? Now, what does it do for us? It means that when we want to calculate all these elements, these integrals, we only need to calculate about half of them. Once you get H12, you don't need to do H21 again. You just take H12 and then put a star that will be H21, okay? So that's safe in terms of computation, that's save half of the work, all right? Similarly, Sji is Sij star. The reason is that I can pretend there is a 1 in between the two-wave function and 1 is a Hermitian operator, identity operator, okay? So again, that saves us work. The third point is that the diagonal H11, H12, things like that, H22, things like that, they must be real because their transpose star equals themselves. So only real number satisfy this requirement, okay? So all in all, I try to convey that it's not as bad as we thought when we want to calculate all this Hij, okay? So we already did that, non-trivial solution, set it to 0. Then we have enough equations to solve for the energies. Then for each energy value, plug it back to the matrix equation and solve for the column vector, eigenvector A, okay? That is really good, formal, but more practically, we will do something lazier, okay? For example, very often, we don't want all the eigenvalues. For example, we only have one particle and we expect that the energy is not that high. So we only want the lower few eigenvalues, the energies. We don't care about the 101 up there, okay? So what to do? The trick is truncate the big matrix as I already did, okay? So how about if you want the ground state one, okay? Maybe you only take 5 by 5 and then get the 5 values, you take the lowest one, that would be pretty good for your purpose. So make truncations. Now, if 5 by 5, you think, that's dangerous. The ground state value may not be that accurate. Good for you. You have that thinking. Make it 10 by 10. Then you compare whether the 5 by 5 and 10 by 10 give you pretty stable, the lowest allowed energy. If that doesn't change, technically that value has converged to its value. So your truncation to that size is already good. Okay, so that is how practically things are going out. Okay, so truncation. And this truncation has a lot to do with approximation methods later on in the second section. Okay, so truncating something is an art and a science. So take home message, we have turned the time-independent Schrodinger equation into a huge infinite by infinite matrix in principle. It is exact, no approximation, all right? Some clever choices make this element simpler. That will save you time, but that is technical, practical stuff, okay? The most important thing is still carry this equation with you. So once you have a choice of basis, I mean this one, okay? This one follows, okay? So at this time, I would like to take a break, okay, since it is 1:18, okay? So let's take a break and then we will resume in about 10 minutes time, all right?